Hello.
Hello, good evening.
Yeah, good evening. Am I audible?
Hello.
Hello.
Yeah,
Yeah, can you hear me?
you're not audible somehow. What did you say?
Okay.
Can you please say again?
Is it better now?
Yes.
Okay. Yeah. And my screen is also visible, right?
Yes.
Okay. So let's start. So today we'll first solve week three's assignment and week three's assignment from last year, and then we'll try to solve as much as possible of week two's and week one's assignment from this year. Okay.
Yeah. All right.
Yeah. Okay. So let's start with last year's week three assignment. The first question is: consider the statement where three coloring is the language that contains all the three colorable graphs, where uh, n denotes the number of vertices. Three coloring is in d space n to the k, and what is the smallest integer k for which this statement is true? Yeah, it's a numeric question. So, what's the smallest value of k?
So yeah. So this is the deterministic space, three coloring, and now since we are talking about the space complexity and we want to decide that whether the vertices are uh, colorable with the three colors or not, and we can do it in the n square amount of the space.
Okay, we can definitely do it in n square, but we can actually do it in order n.
Okay.
Yeah, okay, so yeah, the algorithm is simple. So what we uh, can do is the following. So what we need is the following, right? Or rather, we can. So we can enumerate over all three colorings and check if one of them is is a valid three coloring. Uh, to enumerate over all colorings requires order n space, right?
Yes.
Because like we can have 0, 1, 2 for every vertex, and that's like 2 bits per vertex.
Yes. Yes.
Yeah. And to check if a coloring valid or not. Okay, so now it depends. Okay, so first let's consider the case in which we are given the uh, uh, given the graph as an adjacency list, adjacency matrix, right?
Hmm.
In that case, we don't need any extra space because all we need to do is like for every vertex I, just go over its row in the adjacency matrix and check if uh, the color of the vertex j so that ij is 1 is different from I. So that does not require any extra space, right? For that, we just need to go back and forth over the coloring.
Hmm. Right.
Yeah. And suppose we were given the uh, graph as an adjacency list. In that case, we might need to use order and extra space because when you are given an adjacency list, if you look at, uh, let's say, the list corresponding to vertex I, what would it be? It would be like its entries would be like order log n bit numbers. Each number would represent an index to a vertex, right?
Yes.
So what you can do is copy one such index to the tape, to the work tape,
Hmm.
and use that as a counter to move to the right place in the coloring.
Right.
Right. So this counter takes at most order log n space, right? Hello.
So, but this is the case of the three coloring. So, how much extra space would be required apart from the order of the log n to check that whether the three vertices are not having the same color?
Okay, so we don't need to check about three vertices, right? We need to check only about pair of vertices at a time. So, okay, the coloring is zero. In the coloring, you have zero, one, or two for every vertex, right? What you need to check is for every
Yes,
ij
yes.
such that ij is an edge, the color of I and the color of j are different, right?
Right, right.
So
Clear.
we don't need to check about triples of vertices.
Hmm.
Yeah. So to check if a coloring is valid or not, we need no extra space and uh, graph is given as an adjacency matrix. Order log n space when it is given an adjacency list. Total space is it's order n from here plus order log n, so that's just order n. Is this fine?
Yes, yes.
Yeah. Okay, so let's look at the next problem. Suppose B is a language in NP, and for all languages A in NP, we have that A reduces to B in log space. Then what can we infer from this? Select all that are correct. B is NP complete, B is NL complete, B is T space complete, and B is NP. So which of these are either are correct?
So clearly the option B is correct according to the definition that B is NL complete.
Okay, why? So okay, what's
Uh,
the definition of an NL complete language?
so the say the problem A is in NP and no, A is in NP. I thought that it is in NL.
Okay, okay. Suppose A were in NL. Okay, suppose this were NL.
Yes.
Would B
So
be NL complete then?
okay, so if A is element of NL and all those problems which are there in NL can be are log reducible to the problem B, then the problem B is NL complete, but the problem B itself should be the element of NL then.
Right. So B would be NL hard,
Yes,
but
B would
not
be
necessarily
NL
NL
hard.
complete. Right.
But if B is the element of NL also, if
Yeah,
so here
then it
it
would
is,
be NL complete. But
yeah,
over here, B is an element of NP. Right.
yes.
Yeah.
So now since it is NP, so the problem is trickier now. So
Okay.
yeah.
Okay. So let me tell you what the answer is, and then I can give it explanation. So the answer is B is NP complete.
Mhm.
The reason is the following. Okay, at a high level, the reason is the following: that if A is log space reducible to B, then A is polytime reducible to B. So this is the claim. Okay.
And how is this true that so I mean what is the precise meaning of the term say log space reducible?
Exactly, right. So yeah, that's what I'm doing right now. So if okay, let me write this as a claim. This would so like weren't log space reductions covered in class this week?
So the log space is covered in week 4, the content of the week 4 lectures.
Okay, so I think yes, across two offerings there has been something. Yeah. So what was covered in week three this time? Space
Log,
boundary?
log, log. I mean, this NL and NL complete is in week 4. It is not in week 3, I think. I'm not sure whether it could be in
Okay.
week 3 as well. Yeah.
Yeah, because I think okay, then there might have been something between the 2 weeks,
Yeah.
like between the two offerings. Yeah. So okay, so okay, so uh, A log space reduces to B implies there exists at on x in 0, comma 1 star is in A if and only if f of x is in B. Okay, so now f is computable in log space. So there is a Turing machine that only uses logarithmic space that can compute f, but
Mhm.
a Turing machine that only runs in logarithmic space would also only use like polynomial time, right?
Yes.
Right. So that implies that f is so f is polytime computable, and so a uh, in polytime.
Right. So
Yeah.
is this okay to say that L and NL both are the element are the subset of the P class?
Okay, can you repeat the question?
So L is a subset of the P class, and so
Okay,
is NL.
yes. Okay, so yeah. Okay, so okay, one easy way to see that is that the NL complete one of the NL complete problems is path, right?
Yes.
Yeah, and path is in P.
Yes. Yes. Right.
Yeah. Okay, so then let's look at the next problem. So, which of the following statements is or are true for fn greater than equals to log n? D space fn is contained in d time fn. N time fn is contained in d space fn. D time fn is contained in n space fn. And n space fn is contained in n time fn. So, which of these are correct?
So yeah. So D space and N space is one and the same thing, more or less same. So
Yes. As long as
so
like these quantities are like okay, you are not worried about fine grained complexity. So as long as like these quantities are like okay, so as long as you are worried about only polynomial space and polynomial d space n to the order one and n space n to the order one, you are right.
yes. So
Yeah.
therefore, in this case, the option B and C are correct.
Okay. So yeah, I will get yeah. So okay, what is b n time fn is in d space fn?
So
Okay, right. And use b and
B and C. In the
c.
left hand
Okay.
side, we are supposed to have time.
Okay, left hand side. Okay, right. Left hand side you're supposed to
Yes.
have time.
Yes.
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 Okay. So why is n time fn in d space fn?
Because time can be contained in space and space cannot be contained in time, right? So I
Okay,
mean,
okay, that's not exactly true, right? Because what about this? D space log n is contained in time
uh,
n to the order 1.
yes, so with the login, the things are different because if we have a Turing machine which runs in the space of the order of fn, may require the time of the order of 2 raised to the power fn.
Okay, yeah, so that was my point. Like space can be contained in time, but there must be a big blow up.
Yes, yes, yes.
Yeah. Okay, so but then why is that? Okay, that tells us that okay, time can be contained in space without blowing up the function too much. But why is n time fn in particular contained in d space fn? So, for example, let's say you have an n language L in n time fn.
Mhm.
So you have a non-deterministic Turing machine for that language, right?
Yes,
How would you convert that non-deterministic Turing machine to a deterministic Turing machine which runs in space order fn?
there is some issue with your connection,
Oh, okay.
so I could not hear you, and you were on mute for almost for some time. Yes, yes.
Okay, so is it better now?
Yes, yes, fine.
Okay.
So this n time is contained in the D space. Why so? Because D space is more or less same as well. So I mean, for n time, we have a non-deterministic Turing machine and deciding a string in the time of the order of fn.
Hmm.
And D space, yeah. So, but then the non-deterministic Turing machine. So even if the machine is deterministic, right, and occupying the space of the order of fn,
Right.
so this deterministic Turing machine can take exponential time
Yes.
to execute, right? So
Right.
so clearly, if something is decidable in the time fn by the non-deterministic Turing machine, is decidable by a deterministic Turing machine in the time, say of the order of say 2 raised to the power fn or in the exponential time.
Right. So your argument would be true if d space fn were equal to time
Mhm.
2 to the fn, right? But that's a containment. We don't know if these two are equal or not, right?
Yes, so yeah, so with where is the flaw in this argument?
Okay, so what you are showing is that n space fn is contained in d time 2 to the fn, right?
Yes,
Okay, so
yes.
do the following. You have some conversion from non-determinism to determinism in mind.
Mhm.
And what you're currently arguing is that that conversion only takes a certain amount of time. Now try to argue that that conversion only takes a certain amount of space.
Okay,
Yeah.
okay.
So the conversion you have in mind is correct.
Mhm. Uh, so say according to the Savage theorem, even if the machine is non-deterministic and occupying the space of the order of fn, that
Hmm.
would be more or less same.
Okay, that would be
Every-
order fn square over here, right?
yes, yes.
Yeah. I mean the conversion you had was correct. Okay, let me tell you. So you had this conversion in mind, right? You were non-deterministic Turing machine.
Mhm.
It would make some non-deterministic choices, right?
Yes.
Enumerate over all of those choices,
Mhm.
and this enumeration you can do in dspace fn, right?
Yes.
So what you were saying is this uh, enumeration can be done in time in deterministic time 2 to the fn, right? This
Yes.
is what you were saying, right? But that is when you're looking at time. When you're looking at space, since you can reuse space, you can run this simulation in time. Or okay, you can run this enumeration in space fn, right? Hello.
Again, you are not audible.
Okay,
You
yeah.
were, yeah, you were on mute for some time,
Oh,
and
okay,
your screen was freezed. Your video was
okay,
freezed.
okay,
Yeah.
okay. So what I was saying is, yeah. So you had a simulation in mind.
Hmm.
Uh, that enumeration would take 2 to the order fn time, but
Hmm.
it would only take like order fn space because you
Hmm.
can reuse space,
Yes.
right? So that proves B, and Similarly for C, I mean, if, okay, B implies C, right? Because of this reason. So because of this reason, B implies C.
Correct, correct.
Yeah,
Yes. Right.
yeah. So yeah, okay. So let me just write this in time. Okay, yeah, okay. Let me not write this because yeah, this would be long. Yeah, so
So its
basically it's this. Yeah,
yeah, its explanation is not required, I
yeah.
think.
Okay. So then let's, in that case, let's look at the next problem. The next problem is which of the following is or are definitely true? Select all that are true. N time n time n square is contained in d time n to the 4, n space n square is contained in d space n to the 4, n time n square is contained in d space n to the 4, and n space n square is contained in d time n to the 4. So which of these are, are definitely correct? Hello.
Yeah, so options B and C are correct.
Okay. Why is B correct?
B correct. N space of n square is according to the Savage theorem.
Exactly. Yes.
According to the Savage theorem, yes, yes.
Yeah.
According to the Savage theorem, the option B is correct. And according to C is not difficult to show.
Yeah.
Uh, yeah, so therefore, yeah, B and C are correct, I think.
Okay. Another way to show C is just this, and then use B.
Yes, yes.
Yeah. Okay. So the next problem is consider the problem of adding two n cross n matrices whose entries are 0 or 1, and assume that the two input matrices are given as vectors of length n square each. We need to output the sum matrix. What is the space requirement of the most space optimal algorithm to execute this using a deterministic Turing machine? Options are order 1, order log n, order log square n, order n, and order n square. So, like, which of these is
So,
correct?
yeah, so uh, since I need to find the sum of the two, so I'll go for order of n square then.
Okay, order of n square would be true if you are also counting the amount of space required to output the matrix. But
So, so
the,
basically, I require the log of the n square thing to store everything.
okay, yeah, that's order log n, right?
Yes.
Yeah, yeah, okay. And the answer is, the reason is basically this. So, let the matrices be, let's see, be their sum. What we can do is this, and for all, okay, so I will index the matrices from 1 to n instead of like 0 to n minus 1 for all
Yes.
I comma j in n. We need to compute an output C I j and write it on the output tape, right? So now notice that for this, We just need to we need to enumerate over all I comma j in M and write aij plus bij on the output page, right? This enumeration can be done in order log n time, right?
Yes.
Yeah, so like order log n for I, order log n for j, that gives you order again order log n, right?
Yes.
However, you also need like some counters to go to the right position in A and B, right?
Yes.
Because I've written, okay, so what I've done is I've written I and j on the work tape. I want to go to AI AJ, but to do that, I would have to like decrease I and like, okay, somehow like you go to the right place. I would like, let's say whenever I move one place in a column, I decrease j. Whenever I move to one place in a row, I increase I and so on, right?
Mhm.
So you would need two counters as well, right?
Yes.
Yeah, so to get to we would need.
So will it be of the order of log n time or
Oh, wait. Yeah, this is space. Yeah, so we need a counter that can count to n minus 1 times I plus j. Why? Because let's say you are in the first row and you want to go to the jth position, right? Then you just need a counter that counts to j. Okay. Oh wait, it's not. Yeah, I minus 1 times. So okay, are you convinced that we need a counter that can count up to this number?
so to get aij and bij, we would need a counter that can count to this thing. And how did we get this number? I minus 1 into
Okay,
n
so
plus.
let's say you are in the ith in the first row, right? Then you just need to count to j to go to the 1 comma j position, right?
1 comma jth position, right?
Yeah. If you were in the second row, you would have to count uh, n plus j because you need to clear the entire first row
Uh-huh.
and then move to the second row, right? So
Correct.
the first row would take n, the second row would take j, right?
Correct.
Yeah. So I minus 1 times n plus j can be computed in order log n space. Why? Because like both of these are order log n bit numbers.
Yes.
Yeah. And so yeah, once you compute it for to maintain the counter, you also need just same space, right? The log n space. So total space requirement is order log n. So yeah, like we need three things. One, we need to maintain INJ. Then
Mhm.
from these INJ, we need to compute this number. And once we have this number, we need to use this number as a counter. So all
Yes,
three of these require order log n space, and the combined space uses the order log n.
right.
Yeah. So now let's look at the next problem. The next problem is consider the problem of multiplying two given n cross n matrices whose entries are 0 and 1. Assume that the two input matrices are given as vectors of length n square each. We need to output the product matrix. Uh, what is the space requirement of the most space optimal algorithm to execute this using a deterministic Turing machine? Order 1, order log n, order n square, or order n to the omega, where omega is the matrix multiplication constant. So which of these is true?
So I have a new option here, n raised to the power w. So I don't know what this matrix
Hmm.
multiplication constant is,
Oh, so
but
this is not W, it's omega.
yes, omega. Yeah.
Yeah, so okay, omega is this. Okay, so okay, consider all algorithms for multiplying n cross n matrices, okay?
Hmm.
And look at the algorithm which requires the minimum amount of time.
Okay. Okay. So the current state of the R2 multiply two matrix is
Yes.
somewhere of the order of 2.37, I think.
Okay, so it's not the current state of the art. Omega is like the best over all existing algorithms, so it's like the theoretical best.
Okay. Okay. All right. Yeah.
Yeah. But I mean, that doesn't matter over here because this is a theoretical question, right? So
So
let's say even if omega were 2.1 and the
mhm,
best node is 2.37, we can, in this question, we could still say 2 point n to the 2.1, right?
yes.
Yeah.
So since the requirement is of space, so I think that we can do this in the effort of the order of n square.
Okay. Again, that would be true if you were output, if you considered the amount of space required to write down C,
Amount of the space required for?
okay, amount of the space required to write down the result matrix. But we are not
Okay.
counting that, right? When we talk about space model computations.
Okay. Okay.
Yeah,
So,
so
but
like in
still,
the space
but
model computations, we don't look at the input space and the output space, right? Just the workspace.
yes.
Yeah.
So, yeah, since this is the case of the multiplication, so I need to multiply the things like say, the entire first row
Hmm.
with the first column, and say
Right.
the first row contains n number of the element, and the
Hmm.
first column contains n number of the elements. And so to store these n values, so I'll have to make how many modifications? Say n number of the multiplications for to get one element. So therefore,
Hmm.
the space required, I need to keep the track of all this. So to multiply to get an element of the product matrix, I require the space of the order of n multiplied by something, and what that something is that I have n square number of the elements. So I think that I require the space of the order of n multiplied by log n, and which is not an
Okay.
option here. Yeah. So at least this much of the space is required. I mean, I require order of n amount of the space to keep the track of the number of the products of the first row and the first column. And
Okay. So
then
let's
for
say
the
we are
engine,
multiplying the first row and the first column, right?
yes,
So what we would do is we would iterate over. Okay. So what we are doing is, let's say the matrices are A and B. So what we would do is we would do sum over K, A 1K, B K 1, right?
yes, yes.
So over here, we only suppose we only kept track of K. Would this be sufficient?
So if I only keep the track of the case, yes, that won't be sufficient because I need to keep the track of the okay that can be reused. So because of this reuse thing, it is sufficient to keep the track of the k only, and which requires a space of the order of log n.
Almost correct. You need to keep track of one more thing, and that is the current sum. So let's say k goes from 1 to n, right?
Yes.
You have added the first five elements, so you need to
Mhm.
store that sum somewhere.
I need to.
Store that sum somewhere, right?
Yes, yes, yes,
So you
yes,
need to keep track of two things, k and that sum, right?
yes, yes, yes.
Right. Okay, so yeah, so again,
And
the answer is still order log n,
yes, and for both the
but
things, we require the space of the order of login.
yeah. So there is one more thing. Why can we store the sum in space order log n? Yeah, that is important. Okay, so again, let the given matrices be A and B, and C is equal to A times B. Cij is equal to sum over k 1 to n aij aik for all k in ij in it. So just as before, so like just as before, as in just as in the previous problem, we
Yes,
keep I, J, and a counter that counts to. Okay, okay, now okay, that before the counter, I need something else. Yeah, so we just as in the previous problem, we keep track of I and J, right? But now we also need to keep K. K counters that count to. mm, I minus 1 times n plus k and k minus 1 times n plus j, as well as the partial sum sum n in 1 to k a I l b l j. Okay, so the claim is you need these two count along with k. You need these two counters and this partial sum. So are you convinced why we need these two counters?
yes. But the
Yeah.
thing is that we require to store all these things in a sequence. So therefore, the order of login is sufficient for every counter. I mean, for every I mean every piece of the information we need to
Hmm.
store. We require of the order of login, and we
Yes.
require this thing in sequence.
Right.
Yeah.
So there is one more thing. Okay, I agree that this, and these require order login space. But how can you say that this will only require order login space and not something much more?
Yes. So.
So suppose the sum were to blow up like anything. Okay.
Mhm,
Then let's say the value of the sum became 2 to the n. Then you would
mhm.
need order n space, right? So what we need to do is we need to somehow bound the space required by this. One way to do this is to bound the value of this sum.
Mhm.
So can you upper bound the value of this sum?
Yes. So since the adjacency matrix is a Boolean matrix here,
Yeah, so the matrices are Boolean, right?
yes. So if L varies from say 1 to k, then
Yes.
in the worst case, I need to store say how many, and I can vary from say where to where, say from
Okay, so over here
1
I
to
and J are fixed, right? Because we are
yeah,
computing the CIs here.
yes, yes. So
So we only need to
L
worry about L.
from 0 to, so therefore this is bounded by a value k. At the most, the each value could be
Yes, one.
yes. So this is bounded by
Right.
the value k.
Yes. So maintaining I, J, K and the counters requires uh, order login. Okay, let me order bigger space each. Also this sum is less than equals to L, which is less than equals to N. So, oh, sorry, less than equals to K. So, storing this sum also requires order login space. So, total space is order login. Yeah, is this fine?
Yes, yes.
Yeah, yeah. So now let's look at the next problem. The next problem is which of the following choices is or are correct, and then select all that apply. Path is NL complete, path is co-NL complete, path complement is NL complete, and path complement is co-NL complete. So which of these are correct?
So I know that path is NL complete,
Okay, that
and
is true.
since NL is same as
Hmm.
co-NL, so
Right.
since NL is same as co-NL, so therefore it would be co-NL complete as well.
Yes.
And if path is NL complete, then its
Exactly.
complement would be co-NL complete. So yes,
Right.
all the four options are correct, I think.
Yes. Yeah. And the reason is yes. Uh, NL equals co-NL. Path is NL complete, and L is NL complete implies L complement. Okay, this is familiar. Is co-NL complete. Yeah. Okay, so the next problem is suppose there is a non-deterministic space bounded Turing machine N uh, with the space region of order Fn, where Fn is at least log n, and which of the following constitutes the tightest upper bound for the number of configurations of n? Order Fn, order Fn, Fn square, order 2 to the order Fn, and b to the 2 to the order Fn, where b is the maximum branching factor. So by the maximum branching factor, I mean the like look at all the states of the non-deterministic machine. If from a current state you can go to at most b other states on reading a symbol, the maximum value vector would be b.
Yes, so the correct answer is C, the 2 raised to
Yeah.
the power of third order of Fn.
And why is that the case?
So, I mean, how many different configurations are possible
Hmm.
since the Turing machine is occupying maximum Fn amount of the space? So, for
Yes.
each cell, assuming that the set of the alphabet comprises of two elements only. So,
Okay.
for each cell, we have two possibilities,
Hmm.
and so therefore, for the Fn number of the cells, the number of the possibilities will be 2 raised to the power of the order of Fn, and we assume that the NTM has only one state. So these many different configurations are possible.
Okay. So yeah, what you said is essentially true. So every configuration is state. The contents of all the tape other than the input tape and all the head positions, right?
Yes,
So for state, you need constant number of bits because the number of states is constant. It does not grow with n.
yes,
Uh, like we are only concerned about space usage other than the input tape. So it's like there are only order fn many cells, and so that would only require order fn space to store them. So
yes.
right now it's constant plus order fn.
Hmm.
And for all the head positions, you would require like order log n. Okay, you would require maximum of order log n plus order log fn.
Uh, yes, but then we can simplify this calculation by assuming without the loss of the generality that
Hmm.
the NTM comprises of NT is having only one state, and
Wait, why one state? Like,
because if say if there are even if the set of the states is finite, say assume that
hmm,
is that if there are q number of the possibilities, then the possible configurations would be q into say tau is the cardinality of the set of the tape symbols, say, so then q into tau into say fn. So in that case we would be, I mean, how many total possibilities may exist then for each? Yes, so that would be uh, I mean, how many? Q into tau into. Uh, so the uh, Turing machine is there. So for each cell, we have tau number of the possibilities. So for fn number of the cells, tau raised to the power fn number of the possibilities, and Turing
yes.
machine may reside there in the state, say in one of the q number of the states, and the head may point to one of the fn number of the possibilities. So total configurations possible in that case would be q into fn into tau raised to the power fn. Uh,
Okay, right. And
wherein
tau to the power fn is just 2 to the order fn because
yes, yes.
tau is constant, right?
Yes, tau is constant, so can be so tau, the cardinality of the set, can safely be considered as equals to 2. It's a 0, 1.
Right, yeah.
So yeah,
So it's like something times 2 to the order fn, but you can absorb that something in the constant over here,
yes,
right? So
yes,
suppose it were like n squared times 2 to the n, what you can do is that let's say this is less than 2 to the 4n, something like this, right?
yes,
Yeah, so it's just 2 to the order fn.
correct.
Yeah. Yeah. So the next problem is which of the following is or are definitely true and select all that apply. P equals NP, NP equals co-NP, L equals NL, and NL equals co-NL. So which of these are definitely known to be true?
So I would like to go for C and D. Uh,
Okay, D is true. Uh, how do we know that C is also
so
true?
C is so we can view it in light of the Savage theorem, and so since log is a
Okay, yeah.
special case of the Savage theorem, so uh, it can
Okay,
also
so
be true.
yeah, let me write it down. So what does ah yeah, so Savage's theorem says this, right? Uh, n space Fn is contained in D space uh, Fn square, right?
Yes.
And what is L? So L is d space log n. And what is NN?
So any space of log n?
Uh, okay, so from here, how can we conclude that L and NL are the same? Because like we can't, right? Because you would need log square n instead of log n
So
over here.
while considering this equality, I went for that L and NL would be more or less same, and there won't be much difference. So even if the square thing is required, probably the square won't make much difference. I think space wise.
Okay, so okay, so yeah, so if you want to use Savage's theorem, we would need log square n over here, right?
Yes.
And like that is more space than log n, and we don't
Yes.
know if yeah, if you can do something in log square space, you can also do it in log space.
So can we say that L is more or less or approximately equals to NL? Will that be fine?
Okay, okay, so if you were to like okay, so if for L and NL you allow this extra constants over here, then it would be true. What you said would be true.
Could not understand
Okay,
this.
so if instead of defining L as this, you defined L as and NL is also this, then what you said would be correct. Then L would
Okay.
be equal to NL. Yeah,
Okay. Okay.
yeah, but like both of them are like strictly log space, so yeah, they are not the same.
Clear.
Yeah, okay, yeah. So only D is correct. NL equals co-NL, and that is because of Zimmermann-Selleck theorem. Yeah. Okay, so is this fine?
Yes. Yes.
Yeah. So then let's look at the next problem. So like the polynomial hierarchy is over P and P, co-NP, sigma to P, pi to P, and so on. Let us try constructing a log space hierarchy over L, NL, co-NL, sigma to L, pi to L, and so on. So which of the following statements is correct? The log space hierarchy collapses to a finite level. All the infinite levels of the log space hierarchy are distinct. The log space hierarchy could either collapse or be distinct, but as of today, we do not know which of these cases are true. So which of these is correct?
So I think that since NL is equal to QNL here, so
Yes.
therefore the hierarchy will collapse, and the option A
Yeah.
is correct.
Yeah. So in fact, it collapses to like NL.
Yes.
Yeah. Okay. So that was all the questions from last year's week 3 assignment. So now let's solve questions from this year's week 2 assignment. So we also have questions from this year's week 1 assignment. So do you want to solve that first or these first? Hello.
Yes. Yes. Yes.
Yeah. So we like there are also questions from this year's week 1 assignment. So do you want to solve those first or week 2 assignment first? Because we might not be able to complete both of them in time.
Okay. So let us continue with this week two assignment. No
Okay.
issue.
Yeah.
Yeah.
Okay.
So,
Okay. So the first question is if NP equals co-NP, then it would imply which of the following mark all the correct answers. PH equals to NP. P equals to NP. For all L in the polynomial hierarchy, L reduces to three-set in polynomial time, and P not equals to NP. So which of these are correct?
So I think that except the last one, the first three are correct. A, B, and C.
Okay,
If NP
so
is equal to co-NP, then there would be the hierarchy will collapse. So pH would be equals to NP.
that is true.
And since NP is equal to co-NP, so uh, yeah, so the it shows that P is equal to NP.
Why?
And why so? Yeah, so
I mean, something like that is known, but not in the direction you are saying.
okay, okay,
So what is known is that if NP were not equals to co-NP, then P would not be equal to NP.
okay. And if NP is equal to co-NP, then
That doesn't, okay, so this statement does not imply anything about P equals NP, right?
why
Because
so?
what, okay, so
Because
what we
what's
know is this, and this is equivalent to saying that P equals to NP implies NP equals to co-NP, right? But so this is the implication we get, and in the question we need this reverse implication, right?
okay, yes,
Yeah.
yes.
Okay, so like just because NP not equals NP equals co-NP, we cannot say anything about P equals NP,
Mm-hmm.
at least not yet. We don't have any connection. So B is not true at least as of yet. And what about C for
C will
all?
C will be correct. Yeah.
Okay, why?
So this was based on this thing that P is equal to NP. But so since NP is equal to co-NP and it does not infer anything about the equality of the P and NP, so then I cannot say.
Okay,
Uh,
but we can use option A, right? So pH equals NP. So
mhm.
L is in pH, so L is in NP. And since 3 set is NP complete, LS will reduce to 3 set in polynomial time.
Yes, yes, right.
Yeah, so okay. Let me write it down. A implies. Yes, was this fine?
Yes,
Yeah.
but why this NP is equal to
Yeah.
co-NP does not infer that P is equal to NP?
Okay, so like how would you go about doing
Okay,
this?
so if P is equal to NP, then why the NP would be equals to co-NP? Say, let us consider
Okay.
this then.
So I think we briefly talked about this last time, but we were in a hurry. So I remember, if you remember, I said that for any language L in P, its complement is also in P.
Yes, yes, that's true.
Right. So if P were equal to NP, then let's say L is in NP, therefore L is in P, therefore L complement is in P, and therefore L complement is in NP. But L complement is a language in co-NP, right?
Yes, in that
So every
direction.
language in
Fine, fine. I
co-NP, by
understood.
using this
Yeah.
argument, every language in co-NP would be in P and therefore NP. Yeah, so is this fine?
Yes.
Okay, and okay, so that was about this. How would you prove this?
So if NP is not equals to co-NP, then
I mean, one way to do it is that's just the contrapositive of this.
so if NP is not equals to co-NP, then the complement of a language, uh, yeah, is in P, but then these are two distinct sets. So I don't know.
Okay, so one way is to just observe that this statement is just the contrapositive of this statement, right? So this is P implies Q,
Yes,
and
correct,
this is
correct, correct.
negation
Yes,
Q
yes,
implies negation P,
yes, yes. You're right. Yeah,
right?
yeah.
But yeah, so if you are looking at a direct proof, there is also this direct proof. So NP is not equals to co-NP, right?
Hmm.
Which means 3 set cannot be in co-NP.
Which means
3 set cannot be in co-NP,
three set cannot be in co-NP. Yes, right.
right? So now suppose P were equals to NP, then 3 set would have to be in P.
Yes.
Therefore, 3 set complement would have to be okay. No, wait, not. Okay, so yeah, I mean it's convoluted. Yeah, so okay, so if P were equals to NP, then 3 set would be in P. So 3 sets complement would be in P, and 3 sets complement would be in NP, right?
Mm-hmm.
Okay, so I should have started with 3 sets complement cannot be in NP. So if NP not equals co-NP, 3 sets complement cannot be in NP because 3 sets complement is co-NP complete, right?
Mm-hmm.
So like, yeah, was this clear or should I go over this again?
Actually, it is it's okay that the first result uh, is the contrapositive of the second
Yeah,
one. The second one is well known.
yes,
So, but then I mean, what is the intuition behind this thing? That if NP is not equals to co-NP,
right,
what does it mean? What does it mean that the say if L is the element of NP,
right.
then the complement of L is the element of co-NP, and if both are not equal, then what does it mean that the
So that means that there exists at least one L such that L is in NP, but L complement is not in co-NP, right? Sorry, L complement is not in NP. Yeah, okay,
yes,
let me, yeah,
yes, 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 yes. So it clearly shows that yes. So there exists some L which is
hmm,
in NP whose complement is not there in NP.
right,
So it shows that clearly P cannot be equals to NP then. Yes,
yes, yeah, because
understandable.
both
Yeah.
L and L complement would have to be in P and therefore NP.
Yes, correct, correct.
Yeah,
Understandable. Yeah.
yeah. Okay, so the next problem is suppose there exists a deterministic Turing machine M that runs in polynomial time, a language L such that X is in L if and only if for all U1 there exists U2, for all U3 there exists U4, so that M on input X, U1, U2, U3, U4 is 1, where Ui is in 0, comma 1 to the Q I size of X and Qi are polynomials, okay? So all these four have polynomial size. Where
Hmm.
L is, and select all the correct options, known to be in sigma phi p, known to be in pi 4p, known to be in the polynomial hierarchy, and known to be in sigma 4p. So which of these options are correct?
So I think except the last option, the
Hmm.
first three are correct.
Okay, yeah. So why is this? Okay, yeah, first we are correct.
Yeah. Second one is obviously correct, and it is a part of
Okay,
the PH. Yeah. Last one cannot be correct because it is starting with an universal quantifier and not with the
yeah.
existential one.
Okay, so yeah, so B and C are true. So why is A true?
Because I can always add a dummy existential quantifier in the beginning, and that will
Right.
cause
Yes.
nothing.
Yeah. So in general, sigma IP is contained in pi I plus 1p, and
Yes,
pi IP is contained in sigma I plus 1p.
yes, yes, yes,
Yeah. And if the fourth one were known to be true, then we would have known that pH collapses, but we don't know
yes,
that yet, right?
yes.
Yeah. So we can't say anything about the fourth one. Okay. So the next option is let sorry the next problem is L is in sigma. Let L be in sigma I, where I is strictly greater than 1. If for if for all languages L prime in the polynomial hierarchy, we have that L prime reduces to L in polynomial time, then which of the following options is or are true? And select all the correct options. pH is in sigma I, pH equals to sigma I, P equals to NP, sigma I and sigma I plus 1 are the same, and sigma I and pi I are the same. So which of these are correct?
So, yeah, I think that A and C are correct,
Okay. Yeah, A is correct.
and C will also be correct, and
Oh, sorry,
B,
not B, C.
C.
Uh, yeah,
That's
and okay, so why is B not correct?
so how can this be correct? Because all the languages which are there in PH are getting reduced to L, and L
Right.
is and
So
since I is greater than one.
Right.
So
Yeah. So I mean, even like it might be possible that P1 equals to NP, but whatever is given in the question does not imply that P equals NP, right?
yes, yes.
Yeah. And what about D? Why is that not correct? Or why is that not known to be correct?
So now this would be uh, so yeah, because pH is collapsing at is at maximum this sigma I. So
Hmm. Okay, so you can either prove D using A or C. So pH collapses to sigma I. So pH equals to sigma I. Now pi I is contained in pH. So pi I
uh,
is contained in sigma I, right?
pi I is containing in sigma I. Yes, yes,
Yeah.
right.
But then when you okay, so okay, let me prove D first. A implies B. So pH equals to sigma I and uh, pi I contained in pH implies pi I contained in sigma I, right?
Mhm.
Okay, so now 0, comma 1 star. Okay, let me do it like this. So pi I is contained in sigma I, right? So now sigma I, okay, so pi I is contained in sigma I, but okay, why is sigma I also contained in pi I? Because you want to prove that they both are equal, right?
Mhm.
Okay, so if, okay, what I'm asking is the following. If pi I is contained in sigma I, why is it the case that sigma and pi are exactly the same?
So yeah, uh, it's not that clear to me.
Yeah.
Actually, even though I'm using the term collapse, but I am not pretty sure that what's the meaning of this collapse is.
Okay, so let's say when I say that pH collapses to the ith level, it means exactly this.
So what is the intuition behind this? How to perceive this thing that the pH collapses and then at the ith level.
Okay,
So
so one way to see it is the following that you need at most I level of alternating quantifiers for any statement which requires any number of alternating quantifiers.
okay.
Right,
So the meaning of pH is equal to sigma I here would be that at the ith level we require exactly I number of the alternating
right.
quantifiers.
Yeah, so suppose you had a statement, let's say I were 3, and you had a statement like this. There exists U1 for all U2, there exists U3 for all U4, there exists U5, right?
Mhm.
Then there would be a way of converting this U1 to U5 to just 3. There exists V1 for all V2, there exists V3.
Hmm.
So basically, you can, if you have more than three quantifiers, the alternating quantifiers can collapse them to three quantifiers.
Hmm.
Yeah, so that is what it means to say that, that is what it means to say that pH collapses to the third level. And same for any I.
Hmm.
Yeah. Okay, so is the meaning of pH collapse to the ith level clear now?
Yes, it's
Yeah.
clear. It's clear.
Yeah, so okay, so we have pH equals to sigma I. So okay, so is this clear? Or just
So
this part?
so since pH is equal to sigma I, means pH collapses at the there exists level. So if it collapse at the there exists level, then will it be true for all I also? I mean for all level also, because pi I shall begin with for all for all, and
Yeah, okay. Right. So the meaning of pH collapse is this, right? Hello?
yes, you're
Yeah.
audible.
So the meaning of pH collapse is this, and since but pH also contains pi I, right?
Yes.
Okay, so if you are not comfortable with this, and here's another way to do it. Uh, Pi I is contained in sigma I plus 1, which is contained in pH, which is equal to sigma I. So
Clear,
it
clear.
doesn't, we can just add a dummy quantifier, right?
Yes, yes.
Yeah. So are you okay with this one
Yes,
direction? Okay, so
yes,
now what we want to prove is when if okay, so okay, I have this and I want to prove this. So now what we want to show is if pi I is contained in sigma I, then sigma is also contained in pi I.
yes,
And the way to do it is this: let L be in sigma I, then L complement is in pi I, right?
yes,
Then but okay, L complement is in pi I, which implies okay, L is in sigma I. L complement is in sigma I. Why? Because sigma is contained in pi I.
correct.
And this implies L complement is in pi I. That is L is in pi I, right?
Yes, yes, clear.
And so L is in pi I. And this is true for all L in sigma I, right?
Correct, correct.
Yeah. Okay, so that implies D. So that is also true. Another way would have been to like use C directly. So from C we have sigma equals sigma I plus 1. That would have implied that pi I is contained in sigma I and then use a sigma
Clearly,
argument again, right?
clearly, yeah. So
Yeah,
that is easy to understand. Yeah, true.
yeah. Okay, so A implies, okay, so D, so okay, so what we have shown is A implies D. A also implies,
A also implies C.
yeah, because, yeah, PH, okay, sigma I plus 1 is contained in PH. So, PH equals to sigma I implies sigma I plus 1 is contained in sigma I. But from the very definition of these two, we know that sigma I is contained in sigma I plus 1. So sigma equals to sigma I plus 1, right?
Yes.
Okay, so now we need to prove A, right?
We need to prove what?
A. So why is A true?
So I said A is true based on my intuition that since for I is greater than 1,
Right,
all the languages which are there in PH are getting reduced to this L,
right.
right? So therefore, clearly this, I mean, all the languages in LDS cannot be more complex than the following.
Exactly, yeah.
So
Yeah, so
got
that is the intuition. And to formalize this intuition, we can prove this claim. So if A is in sigma I and B reduces to A in polynomial time, then P is also in sigma I. So this claim captures the intuitive argument you were making, right?
yes,
Yeah, so if B reduces to A, then B cannot be more complex than A, which is in sigma I. So B is also in sigma I. Okay, okay, let me see if this what space is enough or not. Otherwise, okay, let me move this down. Yeah. Okay, so yeah, so B reduces to A in polynomial time implies that there exists computable function f such that for all x in 0, comma 1 star, uh, x is in B if and only if f of x is in A. This is the definition of reduction, right?
Yes.
And A is in sigma I implies there exists a polytime, a deterministic Turing machine M, and a polynomial Q from n to n such that uh, for all x in 0, comma 1 star, x is in A if and only if there exists u1 for all u2. Okay, so there exists u1 in 0, comma 1 to the q size of x for all u2 in 0, comma 1 to the q size of x, so on to qi 0, comma 1 to the q size of x, m on input x, q1 to qi is 1, right?
Uh, yes,
Yeah,
yes.
where q is there exists if I is odd and for all otherwise. Okay, yeah, so this is the definition of A being in sigma I, right? Now consider a Turing machine M prime, which on input x u1 to ui computes f of x and simulates uh, yeah, m on in and simulates this. Okay, so consider this Turing machine. So what it does is instead of when it gets input x u1 to ui, instead of directly executing x on u1 to ui, it first computes f of x and then executes m on u1 to ui. Okay.
Yes.
So now m prime is clearly a deterministic Turing machine. Oh, sorry, a polytime deterministic Turing machine, right?
Hmm.
Why? Because what does m prime do? It first computes f of x, which since f is a yeah, since f is polytime computable, it can compute f
Hmm.
of x in polynomial time. And then
Yes.
when it runs m, now m would run in time polynomial in size of f of x in u1 to ui. But since f of x is polynomial time computable, size
Hmm.
of f of x would also be polynomial in the size of x, right?
Yes.
So the overall running time of m prime is still polynomial.
Hmm.
Yeah, and observe that uh, for all x in 0, comma 1 start X is in B if and only if uh, there exists U1. Yeah, let me just copy this. Okay, so the claim is that this statement is true. That for all x is 0, 1 star, x is in B if and only if there exists U1, U2, there exists U1 for all U2, so on up till UI, M prime on input x U1 to UI outputs 1. So you see why this is true?
Yes, because
Yeah, so it's because of this statement, right?
yes.
Yeah, so basically x is in B if and only if f of x is in A and f of x is in A if and only if there exists U1 to UI so that M on input fx U1 to UI outputs 1, right?
Hmm.
But what does M prime do? When it gets x U1 to UI, it first converts x to f of x and then just runs M on fx U1 to UI, right?
Hmm. Right.
So this implies M on fx U1 to UI is 1, right? But that is exactly what M prime does.
This is exactly.
What M prime does,
Yes, yes.
right?
Right.
Yeah. So that's why like this is true. So basically by using M and the reduction function f, you can construct a Turing machine which satisfies the conditions of B being in sigma I. Yeah.
Yes, it is otherwise clear from the intuition as well. However, this is
Yes,
a more
yeah.
formal way of writing this here.
And the intuition sometimes fails when like you, so for polynomial time reductions it's mostly fine, but it sometimes fails when you have log space reductions and things like that.
Again, video got freezed
Oh
and
yeah,
audio
so
too. Yeah.
okay. Yeah, so this intuition almost always works when like the reduction in the classes are appropriate. So for example, if you are talking about polynomial time reductions and PH, it would work.
Hmm.
If you are using space like polyspace or log space reductions and log space or polyspace classes, this would work. This intuition only like sometimes fails when you are talking about say log space reductions, but time. Okay, so you are talking about space bounded reductions, but time bounded classes or time bounded reductions and space bounded classes.
Yes,
Yeah, so when like this type of classes and reductions are different, you need to be a little careful and yeah, in that case like formal things help.
clear. Yeah.
Yeah, yeah. Okay, so then let's look at the next problem. The next problem is which of the following languages are known to be co-NP complete and select all the correct options. Tautology, subset sum, recolorable, or click. So which of these are correct?
So I can only think of the tautology,
Yeah,
and uh, uh, I have not heard that whether this. I mean, the remaining three problems are there in co-NP. Cannot be like say click cannot be in co-NP because its
right.
complement cannot be in NP, and same is
Okay.
true with for the three colorable as well.
Yeah,
And for the subset sum also, because subset sum is more or
yeah.
less same as the Hamiltonian. We used to reduce the uh, subset sum problem to Hamiltonian, I think, or I don't remember. We used
I
to
mean, you
reduce.
can obviously reduce them because all of them are NP-complete. It's
Yes,
just that it depends on which reduction you have seen.
yes, yes, yes.
I don't remember which I have seen for subset sum. I think it was from some version of 3SAT.
Yes, so we used to use subset sum to reduce it to get for the I don't remember for Hamilton for traveling salesman problem. I think I don't remember correctly. For traveling
Yeah.
salesman, probably we use Hamiltonian circuitry, but then we
Yes.
use subset sum for a very well-known problem, and I don't remember which that well-known
I think you
problem
can use it
is.
for knapsack.
Yes, for knapsack, correct. You are
Yeah.
right.
Because I think
Yes,
subset sum is a, yeah, it's a very sort of a very special case of knapsack.
yes, you're
Yeah.
right.
Okay, so yeah, the next problem is P is contained in NP intersection co-NP. Is this true or false?
So it's true because there would be a portion of the NP thing whose complement would also be contained into in the intersection portion, because the entire intersection of NP and co-NP cannot be equals to P. Only a subset of
I
that
mean, we
intersection.
don't know whether it's P, right? I mean,
Yes.
it might be P, we don't know.
We don't know. Yeah, so
Yeah.
therefore it's true.
Okay, so, but why is this true? So we know that P is contained in NP.
Yeah.
So this would be true if P were contained in both NP and co-NP, right?
Yes,
So we know that P is contained in NP. Why is P contained in
we know
co-NP?
that
So we know that P is contained in NP. Okay.
P is contained in NP. P is also contained in co-NP, but then P
Oh,
is something who's complemented also in P itself. So therefore, this cannot be. We do not know that whether this entire intersection belongs to P or not.
yes. What I'm asking is, how do you prove that P is contained in co-NP as well? Because
Uh,
P contained in NP follows from the definition of P and NP, right?
your video actually frequently is getting freezed
Okay.
and audio too.
Okay, so let me try to reconnect.
Uh, some issue of connectivity from my side. I don't. Uh, so then your voice come. I mean, after some time, uh, it comes abruptly. I mean, then
Okay.
then so what
Okay.
did you say that
Yeah.
this
So
is
I
a
was
well-known?
saying, yeah. So okay. So I was saying that P is contained in NP. That we know,
Hmm,
right?
yes.
So how do you prove that P is contained in co-NP?
So P is in co-NP because the complement of NP
Mm.
is in uh, no, not the complement of NP. So P is the element of NP and P is the element of co-NP because the complement of P is
Right?
equal to,
Yes. Yeah. So
because
it's
the
basically
complement of
this.
P is equal to P, so therefore P is the element of NP as well as the element of co-NP.
Yeah. So P complement is contained in NP. Okay. I shouldn't say P complement. Yeah. Co-P,
Yes.
not P complement. I should say. Co-P is so yeah. Co-P is contained in NP. And so P is contained in co-NP.
Co-NP.
Yeah.
So since P is contained in NP, P is contained in co-NP, so therefore P is clearly contained in the intersection of NP and
Yes.
co-NP.
Yeah. Okay. So the next problem is the statement SAT is NP complete is also known as which of the following?
Yes, this
Cook-Levin theorem.
is Cook-Levin theorem statement.
Yeah. So was has Lardner's theorem been covered yet?
Yes, it is covered that you require log
Okay.
n amount of more space to, I mean, the in the time hierarchy.
No, no. Lardner's theorem is something else. Lardner's theorem says that if P not equals co-NP, then sorry, if P not equals NP, then an NP intermediate language exists.
I think this has not been covered.
Yeah, I think that it would be covered now.
Okay, okay.
Yeah,
And
that's what.
Baker-Gill. So what's the statement of the Baker-Gill Solvay theorem then? Is this
Okay,
that
so
for the time constructible function we require log n amount of the more thing to?
no, no, no. That is okay. So the theorem you're talking about is called the time hierarchy theorem or the deterministic time hierarchy theorem.
Yes.
Baker-Gill-Solvay theorem basically, okay, very roughly, Baker-Gill-Solvay theorem says that you cannot use uh, diagonalization to prove that P not equals NP.
To prove,
That P not equals NP.
okay, okay,
So basically, what we use to prove that alt is not recursive, the same technique cannot be used to prove that P not equals NP.
okay.
Yeah. I think both Lardner's theorem and Baker-Gill's theorem will be covered in one of the either this week or next week. Yeah.
Okay, okay, yeah.
Yeah.
So is this possible that in one of the session you briefly explain the diagonalization thing, because it is being so very frequently used, and
Okay.
so
Yeah. So okay. So when
understand.
is so when is the deadline for this week's assignment?
I don't remember.
Yeah. Because so what I was okay. The reason I asked this is the following. So in the first 2 weeks, we did not have any previous assignments to cover, right?
Yes.
So if we get a similar week again, then
Yeah.
either I would add some extra questions or I can use that time to just cover something like this.
Okay. Okay. Okay.
Yeah.
Yeah.
So I think in one of the, I remember that seeing that there would be one more such week. Yeah. So either the next week or the next week, you would be in a similar situation. In that case, I can cover that.
Okay. Okay. Yeah.
Yeah.
Because that diagonalization thing is very difficult to understand, and its use is everywhere. So
Okay. Yeah. Okay. So
even when I listened that proof of the halting problem is undecidable, the
okay.
Sir
Right.
proof. So even though I was able to convince myself that at the end we reach to some kind of the contradiction which can never
Hmm.
happen, but then I could not comprehend that proof. I mean, wholeheartedly. So
Yeah.
because
Yeah. That I agree.
and
So
then when I googled more about the proof, then at many places I found that it is based on the diagonalization thing, and
yeah.
I could not truly understand that what is the use of the diagonalization there. So
Yeah. Okay. So one thing what we can do is whenever these like this theorem is covered, I can cover diagonalization in that week.
okay, all right, yeah, perfect,
Yeah.
perfect,
Yeah.
perfect.
Okay, so the next problem is which of the following is the negation of for all x there exists y phi xy. There exists x for all y phi xy complement. For all x there exists y phi xy complement. So there exists y for all y phi xy complement, and for all y there exists x phi xy complement. So which
So
of
it's
these is
it's
correct?
it's it's C. It's just a minute, not
Yeah.
C. But then there exists, and then for all y, it is A.
Yeah, it's A. So what you do is like basically flip all the quantifiers and put like take negation of every formula.
Yes.
Yeah. Okay. So the next problem is consider the following language. And so by this notation, I just mean the Boolean encoding of a formula.
Hmm.
So the Boolean encodings of our formula phi, so that for all x1 there exists x2. For all x3, phi x1, x2, x3 is 1, where phi is a Boolean formula, and select all the correct options. L is pi 3 complete. L is in pi 3. L is sigma 3 complete. L is in pH. L is pH complete, and L is in sigma 3. So which of these are correct?
So clearly L is in pi 3,
Yes, that is true.
and I do not know whether all the problems which are there in pi 3 are getting reduced into this problem or not. So how can I
Okay.
make the statement in the given in the first
Yeah.
option?
So
And the remaining three options are not correct.
wait. Okay. So why is L not in sigma 3? Because if it were, then pH would collapse, right?
Yes.
And okay, L is not pH complete. Okay. So
Uh,
when
L
can
is
a pH complete language exist? So it's a slightly different question that I'm asking. But the question is, when can a PH complete language exist?
so all the languages which are in PH are reducible to. I mean, there should exist one problem which is
Hmm.
PH hard, and to get that thing, that all the problems which are there in pH hard. So because there are two peaks in the diagram, so if pH complete exists in that
Right,
diagram, we have one peak for sigma and then
right.
other overlapping peak for pi. And
Yes,
if pH complete exists, then both the all the peaks should be at the same level somewhere.
Right.
So that will
And what does
indicate
that
that the
mean?
pH collapses.
Yeah, pH must collapse to some level.
Yes, yes.
Yeah. Okay, so B is true. A is also true. I thought this was covered in class, but okay, so the reason is this. Okay. Yeah. Yeah, so if it is not covered, I can quickly prove this. Okay, so we want to prove that this is pH complete, right? Sorry, pi 3 complete. Okay, let me just say L is pi 3 hard because we already know L is in pi 3. So all we need to prove is that L is pi 3 hard, right?
Yes.
Okay, so let uh, L prime be in pi 3 and there exists mm, polytime.
But I have to say something that
Yeah,
don't you think that this formula is similar to the satisfiability problem only? And since
yeah,
satisfiability is NP complete, so but with some few more quantifiers. So basically, this Boolean formula is satisfiability analogous of the sigma 3. So
yeah.
we are,
So yeah, the proof is going to do exactly the same thing. In fact, it would heavily use the idea of the Cook-Levin theorem, that proof. It would basically use that as a black box.
okay, okay, okay,
Yeah.
yes,
So then there exists a polytime deterministic Turing machine and polynomial Q from n to n for all x in mm, x is in L prime. There exists U1 for n into the Q size of x or uh, n x U1 U2 U3 equals 1. So this is just a definition of something being in pi 3, right? Now,
yes,
using the ideas. Okay, okay, let me first do it like this. Let Mx be a Turing machine that on input U1, U2, U3 executes or simulates uh, Mx, U1, U2, and U3. Okay, so basically Mx is just M, but with X hardwired into it. Okay,
yes.
yeah. So it only needs to take three inputs, not four inputs, right?
Mhm.
Yeah. Now using the ideas in the proof of the Cook-Levin theorem. We can construct a Boolean formula phi such that phi of u1, u2, u3 is true if and only if mx u1, u2, u3 is 1 in
Yeah.
polynomial time. Okay, phi. So this polynomial in polynomial time.
So what is written in the subscript of M? What is M
Eh,
infinite? Or?
oh, no. This is m subscript x.
Okay, yes,
Yeah.
yes.
So yeah, like mx is just a deterministic Turing machine which takes some inputs, right?
Hmm.
And you like in the Cook-Levin theorem, we saw how to convert a deterministic Turing machine that takes some additional inputs into a formula, right?
Hmm.
So using that, we can convert mx, which is just m hardwired with x, into an equivalent Boolean formula, right?
Yes,
And now phi is 1 whenever mx is 1, but mx is 1 whenever m is 1. So we get this, right? Okay, let me call this phi x, 0, comma 1 star, x is in L prime. So x is in L prime if and only if this is true. But if this is true, mx of u1, u2, u3 must be 1. And so that would imply, yeah, I'm just going to copy this. Yeah, so we get this, right?
yes,
So, but given x, we can compute phi x in polynomial time, right? Because all we have to do is convert mx into a formula using the ideas in the Cook-Levin theorem, which we can do in polynomial time, right?
yes, yes,
Yeah, also, okay, so basically this means that this function that maps x to phi x is polytime computable, right? Yeah, so the function mapping x to phi x is polytime computable as well as the double implication holds, right?
mm,
Yeah, so that would, and that is exactly what we mean by polynomial time reduction, right? But there exists a polytime computable function, so that this double implication holds.
yes.
Yeah, and now this phi x is an instance of L, right?
Mhm.
Okay, it's not exactly an instance of L. You need to just write it in its Boolean form, but like as a bit string. But yes,
Mhm.
yeah. So is this fine, or should I go over
Yes,
some parts of this again?
yes, yes, it's clear. It's clear.
Yeah.
The genesis is clear. And so, how difficult it is to formulate a solution if you have intuition of something? So, how
Yeah.
difficult this process of converting intuition into a formal proof?
So it depends. So for example, if you have if you practice a lot, okay. So let's say if you practice these type of things a lot, then it becomes very easy.
Mhm.
Yeah. But okay. So okay, at least for me, this skill does not like transfer to different subjects. So for example, If I've become very good at converting intuition to a formal proof in complexity theory, does
Mhm.
not necessarily mean that I would be immediately able to do it for some new subject that I'm trying to study. So I would have to practice a bit on like solve some problems in that subject, and then I would also be able to do it in that subject.
Yes. Okay. Yeah.
Yes, but at least for me, it's like it requires some solving some problems from that subject. Yeah,
Mhm. Understandable. Yeah.
yeah. Okay, so let's look at the next problem. So, which of the following Boolean formulas are in the language tautology and select all the correct options?
So clearly, the
Option,
option one is a tautology,
yeah, one is the tautology.
and
Uh,
I'll have to check the other solutions. So, uh, yeah. So if it is
okay, let's
true,
go option by option. What about B?
B would also be tautology.
Okay, why?
So if we pick the value of x1 as say true,
Hmm.
so then I'll have to if x1 is true and say so if I pick the value of x2 as false,
Right.
so this will become this is not a tautology.
Yeah, okay, is not a tautology.
Uh, and third one is a which is sort of the tautology. Third one is a tautology.
Yeah, it
I mean,
is.
uh,
Yeah, x1 equals, okay, so B is not a tautology because x1 equals 0 and x2 equals 1 is not a satisfying, right?
yes, C is a tautology and D is also a tautology.
Yeah,
A so ACD.
yeah, so C is, okay, so C is a tautology because what you can do is, so C is just this.
A only.
Wait, so C is this, right? Y complement or Y, where Y is x1 and x2. So C is equivalent to this, right?
Yes.
And Y complement or Y is a tautology, right?
Mhm.
So this is one way to see that C is a tautology. Another way is like, regardless of what you pick, x1, x2, or x3 to be, either this would be true or this would be true, right?
Correct.
Yeah. Yeah. So C is also a tautology. And what about D?
D is clearly a tautology because
Yeah,
the yeah
these ones.
because of these ones.
Yeah. Okay. So the next problem is a k-partite graph is a graph whose vertices can be partitioned into k different parts, V1 to Vk, such that the graph induced by each Vi is an independent set. Uh, this k-partite is select all the correct options. NP complete for k greater than equals to 3. In P for k less than 3. NP complete for k greater than equals to 2 and not in NP. So which of these are correct?
So here Vi is a graph induced by the each Vi is an
No, 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 no.
independent set. So
Yeah. So
so
okay. So
since
Vi,
since I have k number of the independent set problems here,
right?
and each independent set is NP complete. So
Okay,
if
okay,
I have
okay.
been
So
given
I
k
think
number of
no, no. The
k
question
number
doesn't
of
say that. What the question says is the following. Suppose you had a graph. It asks if you can partition it into k sets so that
Mhm.
each set is
Each set is an independent set.
yes, yeah,
Yes, so solving independent set problem is NP complete.
okay. Wait, but
So
how does independent set reduce to
because vertex say click problem, getting
yeah,
the
independent set
independent set.
is NP complete. I agree to that, but it's only NP complete when you ask a question of the form: is there an independent set of size at least k, right?
Yes.
So over here, you are given V1 to Vk. You have to find if V1 to Vk exists.
Uh-huh.
But like, how are you going to say, okay, does there exist a V1 with size at least something, a V2 with size at least something, and so on?
Uh, I'm not asking a. Can you hear me because their video is
Yeah.
freezed?
Hello?
Okay. Can you
Yeah.
hear me?
Yes, I can hear you.
Again your video is freezed. Can you hear me? Oh, you are on mute, I think. Okay, all right, fine, thanks.
Yeah.
So even if this has not been posed as a decision problem, but still this the problem comprises of say k number of the independent sets,
Okay.
and deciding that whether this partition itself is this partition is indeed an independent set. I mean, this problem is NP complete. So I think that since we have to solve k number of the NP complete problems, so the option A is correct for the values of k greater than or equals to 3, and for the values of for the value of k less than 3, wherein we have been given only two vertices, so we can be verified in the polynomial time, and then we have to solve say because because it is in P if the value of k is less than 3. We have been given only two vertices.
No, no, we are not given two vertices. We are given n vertices, and we have
We are
to check if
yes we have
they are partitioned into two independent sets.
Uh, okay. So K is
Number
the
of
number of the
sets.
independent sets.
Right.
Okay. All right. So yeah, so I will not go for the second option then, and the value is NP complete for the value of k is greater than or equals to 2. It is still NP complete for the value of k is greater than or equals to 3, and so I'll go for the options A and C.
Okay. A is correct. Okay. Now let's look at C. So let's fix k equals to 2. So when k equals to 2, does this problem resemble some problem that we already know?
So this is, I mean, it is
The
given in the
problem
problem
of,
that this is of bipartite graphs,
right,
and I can solve bipartite in the polynomial time.
right. So when, so then this is true, right?
Why so? Why so?
So if k is, okay, if k is 1, oh, wait, so the graph isn't, okay, okay, k equals to 1 is simple, right? There cannot be any edge in the graph.
If k
Okay,
is equal to 1,
so the case when k equals to 1 is simple because then the entire graph has to be an independent set, right?
yes,
So
correct,
all
correct.
you have to check is there are no edges,
Yes.
which can do in polynomial time.
Hmm.
For
Correct.
k equals to 2, this problem is deciding whether the graph is bipartite or not, which we saw, I think, in the first week how to do in polynomial time, right?
Yes, so that is solvable in the polynomial time. Correct.
Right. Yeah. So, but for k greater than or equals to,
Again, your there is some issue with your audio.
okay,
So k is equal to 2, it's fine, but then k is
right.
greater than 2.
K is greater than 2, it's NP complete. And the reduction, okay, since it's NP complete, you can obviously reduce from independent set, but the most natural reduction is from K coloring.
Okay.
Yeah. So 3 coloring is NP hard, right? Similarly, K coloring is also NP hard.
Uh-huh.
Yeah. And the okay, so the claim is this.
So which options are correct here? A, B,
A
and then
and
C.
B.
Why not C?
Oh, because for K equal, okay, so this is greater than equals to, not right. So 2 is also covered in this case.
But what if the k is greater than 2 in this case? So it will become an
Right, right.
option B only.
Yeah, so okay, so this is this, right? NPC for K greater than 2, right? So if I were to like expand the statement out, I would do it like this, right?
Yes.
But the first part is not true.
Okay.
Yeah,
Correct.
so
Correct.
if this
Understood.
were strictly greater than, then you, yeah, this would be true.
Yes. Correct. Understood.
Yeah.
Yeah.
So claim 4, G is in K colorable then only if G is uh, K per type, where K per type. Yeah, so this is the claim. So first of all, if we prove the claim, then do you agree that we have shown that it's NP complete? I mean, it's obviously an NP because if I give you the K independent like sets, you can easily verify that, right?
Yes.
So the problem is clearly an NP. All we need to show that it's NP hard. K colorable is NP hard. So if we show this, do you agree that the problem is NP complete?
Yes. So, but then how are we relating this K colorability with the K
K
partition?
part. Yeah, so that would be the proof. But yeah, if we prove the claim, then you are fine, right?
Yes.
Okay, yeah. So let's see why. So the first is G is K colorable. G. So if G is K colorable, then every vertex you can color with like okay, let me write that easier.
So entire graph can be painted with maximum K number of the
Right.
colors.
Yeah. Then yes, I'm just assuming that the colors are 1 to K. Okay.
Okay. Yeah.
Yeah. PI and okay for all I in K. Okay, so what I'm doing is I'll define the set Vi to be all the vertices whose color is I. Okay.
Yes.
Even each and every Vi is an independent set. So do you see why?
So yeah, this is not clear that why. So inside this VI, we have all the vertices whose color is I,
So
whose
they have
color
the
is
same color, right?
yes same color. But then
So
this is not the case.
okay, so suppose Vi was not an independent set, then there would exist two vertices, let me call them U and V, with an edge between them, right?
Hmm. Hmm.
Yeah. But since U and V have been given the same color, this would imply that the coloring we are looking at is not a valid tree coloring. Is not a valid key coloring, right?
It is somewhat clear to me, but not
Okay.
completely clear to me.
Okay. So okay, is not an independent set. Okay.
So we do not find the edges among the vertices in that set.
Oh no no.
So
So suppose
none of the vertex in that set is connected to any other vertex.
no no. So okay, that is what we're going to prove, right? So what we are starting with is suppose V1 was not an independent set. It's contradiction.
Okay.
And we
Okay.
will show that this would lead to a contradiction, and that would be it, right?
Okay. Okay.
Yeah, so
Okay.
suppose V1 were not an independent set.
Mm-hmm.
Then there must exist U and V in V1 such that
Mm-hmm.
U and V is an edge, right?
Mm-hmm.
But the color of U is I, the color of V is also I, right?
Mm-hmm.
But then since we have an edge between two vertices of the same color, the coloring we started off with cannot be a valid K coloring, right?
Correct. Correct. Again, you are on mute.
Yeah, so that would contradict this, right?
Yes.
Because we started off with a valid K coloring, right?
Yes.
So is this fine? Hello? Hello? Hello, can you hear me? Okay, okay. Yeah, so is this fine?
Yes, it's fine. It's fine.
Yeah. And yeah, the other direction is also almost the same. Yeah, so the claim is, so now what do we have? We have K independent sets, V1 to Vk, right?
Yes.
Yeah, and what I'm saying is, let's color every vertex in Vi with the color I. Okay.
Mm-hmm.
So now, first of all, this gives a K coloring because, yeah, there are only V1 to Vk, right? So every vertex has color 1 to I. All we need to check is, all we need to check is whether this is a valid K coloring, right?
Mm-hmm.
Is the following. Uh, Suppose U and V is an edge, right?
But then, don't you think that this is clear that if V is the element of the Vi, then clearly all the vertices are not having any edge in
Exactly,
V.
yeah. Yeah, so that's the argument. Because if there were pick any edge U comma V,
Uh,
both U and V cannot be in, they have to be in different VIs, right?
yes,
And therefore
yes,
get different colors.
yes,
So this is the valid coloring, and it only was K color, so it's a valid K coloring.
yes,
Yeah,
yes,
so that proves A. Yeah,
yes.
yeah. So okay, so we are out of time. Okay, so if you have any doubts in these two questions, you can ask me.
So we have already solved this question in the previous
Oh, okay,
session,
right. Yeah, yeah,
and the last one is which of the following problems are NP complete? So yeah, so NP complete 5 set and deciding if an given undirected graph
right.
has a
Yeah,
Hamiltonian, yeah.
yeah,
So and given so for this AKS algorithm exists for the last D
right.
part.
Yes,
So it's, I mean, yeah,
yeah,
solved.
yeah. Okay, so week one's assignment is still remaining. Let's see if we can fit it in some other week.
Yeah.
Yeah.
So are you conducting problem solving session for some other subject also in NPTEL
Okay,
this time?
not this semester. Yeah. So every semester I only have one course.
Okay, okay, all right.
Yeah.
Yeah, I think we have our assignments on every Wednesdays, right? Deadlines. I was also
Okay.
there. I was like listening to whole thing.
Okay. So yeah. So then what we can do is like in every yeah. So since we have lectures on Tuesday, we can like cover last week's assignment every next week. Yeah, that can be done.
Okay, yeah,
Yeah.
you have done really well. I was listening first
Yeah.
time today,
Okay.
so yeah, it was very nice. I'll try to be regular.
Okay. Yeah.
I had a
Yeah.
doubt in the last question. It was
Okay.
like all the SAT are NP complete, right? Last question. That's how we
Okay.
have
This
learned,
one.
till now.
Okay.
Yeah, the
All the
12th.
set except one set and two set.
Ah, that is a doubter because I thought why that 2 SAT is not NP complete. Okay, got it.
Okay. Yeah. So there is an algorithm, but yeah, it would, yeah, covering that would take time.
Okay.
Yeah.
So that is why 2 SAT is not the answer. Got it.
Yeah.
Yeah, you're doing really well. I'll try
Yeah.
to be regular. I'm also
Okay.
learning so much from this.
Yeah. Okay. So if
Yeah,
there are no other
thank you so much.
questions, we can, yeah, end the meeting. Yeah.
Thank you so very
Yeah.
much. Good
Thank you.
night. Bye.
Bye.
Thank you.